All right. So now I'm feeling good, and I'm ready to uh, feel bad. So let's keep reading a technical book. It's pretty good. Especially when put together with ChatGPT. I kind of made a big discovery in the last video. I was learning about latent spaces, which is a you can think of it like this. Say you're at a costume party and people are all dressed like pirates at the costume party. A friend calls you, they say, "Hey, so my other thing fell through and I can go now." But they have no idea what the event is. You just said, "Oh, you want to come to this event to me tonight?" They call you and they say, "Hey, I can finally go. What should I wear?" So the data is all the people at the party. The encoder is you, and then you encode the data. You encode the information of the people at the party, and then you create a latent space, and then you pass this latent space onto the decoder, your friend. They decode that latent space. Oh, well, everyone's dressed up as pirates. It's a costume party. Great. I'll dress up as a pirate. And that's what a latent space is. It's that, okay, not everyone's dressed up as a party. Some people just didn't put on a costume. Some as a pirate. Some people didn't put on a costume. Some people isn't dressed as the same kind of pirate. But you can create a latent space and accurately describe it as a costume themed party centered around pirates in such a way that if your friend shows up, they will be dressed in a way that they fit in to the party. So why is this relevant? Recommendation algorithms. When you watch a set of movies, what Netflix can do is they can say, well, you watched a romantic comedy, you watched all of these different things, but most of what you watched were horror movies. So I think, based on what you've watched, kind of a lot of bad low rated horror movies, you might enjoy this really highly ranked one. So those are latent spaces. That's kind of why music has been so crazily labeled into genres. You've got fusion, you've got jazz fusion, you've got all these crazy different subcategories of genres, because those basically are latent spaces. So it allows a recommendation algorithm to make suggestions based on this largely diverse data set. You can distill it down to a latent space and and make decisions, because AI is all about automating decisions based on this latent space that is good enough to get a desired outcome. And the big breakthrough I had was that I learned that whole pirate analogy by asking ChatGPT. I said, explain latent spaces in a way that doesn't bore me to death, because I was getting really bored, and it did that, and I learned about latent spaces, and I think I have a fairly accurate view of it. Let me know in the comments if it's completely off. But all right, so continuing on. So this is and there's some on the other page. This is a strategic view of deep learning for network and cloud ops, or network and cloud IA ops. In the previous section, we explored a few techniques that leverage deep and large neural networks. If we look at the most commercial AI ops implementations, we will mostly find unsupervised and somewhat basic supervised techniques, but rarely anything that leverages deep learning. And there is a reason for that, stemming from the fact that in networking and cloud, most of the infrastructures are snowflakes. I'm not saying this in any negative sense, just stating a fact that there are so many technology options and approaches to building networks and types of networks that ultimately Every infrastructure is designed, built, and operated differently. However, however, how is this related to the machine learning discussion? This heterogeneity and disparity of designs imply that, with few exceptions, it is complicated to build generalizable use cases. For example, models with labeled data. Let's take specific labeled data from one service provider network and build a model to predict some behavior. There are very few chances that the model will generalize to other networks in other service providers or enterprise networks. There are exceptions to this, to network, cloud, or IT domains that have been strongly standardized and its interfaces and design principles became more widely adopted. Examples such as 5G access, Wi-Fi access, among others, represent a much richer opportunity for supervised learning-based use cases. However, let's look at a more profound transformation which will impact networking and clouds. In exactly the same way it impacts other knowledge domains. For any such domain, driving, building a car, operating a network, etc., specific knowledge is required to perform any of the tasks within the such domain. If we assume no data is available, human domain expertise is the only source of knowledge to execute such tasks, potentially compiled or captured in rules. As more data becomes available, let's suppose more data collection and instrumentation mechanisms are deployed, it is more and more likely that part of the knowledge required is extracted from the data using different machine learning techniques. This is effectively what we see today in network or cloud infrastructure operations. Human-based rules are complemented with specific machine learning techniques such as anomaly detection, prediction, and clustering, which leverage the data available, frequently with unsupervised techniques. As more and more data becomes available, a more profound transformation will happen with exponential impact. Progressively, the amount of data available is so large that we can start applying deep learning techniques to them with a self-supervised approach to extract a large amount of knowledge from the data itself. The depth and quality of the knowledge extracted are such that the requirements for human domain expertise are reduced, and in the limit, they vanish for basic tasks. The most transformational breakthroughs in fields such as natural language processing or speech recognition did not happen by leveraging linguists' domain expertise, but by leveraging deep data techniques and vast amounts of data. All right, and I've got to advance it. I need a quick pause. I'll pause it and be right back. All right, so I'm back, so let's keep going. So this is a profound transformation in how knowledge is created, particularly affecting its economics. Knowledge is exponentially extracted from data. This is particularly important in the context of network and cloud operation because it will be the only economically sustainable way to deal with the increasing complexity and tightened SLAs required from the infrastructure. Deep learning enables new forms of operational knowledge creation. We will see some examples of it later in the book that will accelerate the adoption of more autonomous decision processes. I have tried to capture the above in what I refer to as the knowledge creation map. For any knowledge domain, the total available knowledge is a combination of the knowledge driven by the human domain expertise and whatever additional knowledge can be extracted from the data. As data becomes more pervasive and deep learning techniques become feasible, the contribution of the data driven knowledge grows exponentially, since now there is a vast amount of knowledge encoded in the data waiting for the algorithms to extract it. We could consider certain domains already in such a far right area of the map. Natural language processing or image processing has such a large amount of data available to process that there are lots of examples of use cases where there is no need for human expertise anymore. And those problems can almost entirely be solved with deep learning models. On the other hand, our networking and cloud industry is pretty much on the left side of the map for the most part. Either we still need more data, or even if there is data, it is presented in such a highly fragmented way or with very heterogeneous data models that prevent proper aggregation and analysis. That means we are still very much in the infancy from a perspective of the application of ML techniques, but that in fact is good news because we still have a tremendous opportunity ahead as data becomes more available for analysis. So now we've got another graphic. We've got a knowledge creation map. So we've got rule-based knowledge. We've got other kinds of knowledge. So I will ask ChatGPT about this. Usually has pretty good answers. And as I mentioned at the beginning of the video, it gave me the party analogy. So just takes a while for it to generate answers sometimes. And it looks like my internet isn't loading it. I think it's on their end actually. So I don't know what Maya is. Oh, you know what? It looks like Maya is the built-in version of voice to text. No, okay. Maya is broken. So let's see here. Paste that in there. And let's see what it has to say. Oops, and I don't need to listen. I don't need to have it listen. I just need to hit enter. This is such a red flag, self-driving cars. It's one of those things that
unusual activity has been detected from your device. Try again later.
Like we're always
882 B8 51C 142 CBADFW.
We're always going to have self-driving cars just a few years, 5 years from now. It's just one of those things.
The diagram you provided represents a knowledge creation map in the context of advancements in artificial intelligence and data science technologies. It visually illustrates the relationship between the availability of data, human expertise, and the evolution of AI capabilities over time. Let's break down each element of this diagram. Components of the diagram. X-axis, time and technological evolution. The X-axis represents time and the evolution of AI technologies, ranging from legacy IT monitoring tools to current general AI, ML capabilities, and extending into future technologies like self-driving cars and sophisticated natural language processing applications. Y-axis, knowledge creation. This axis measures the ability to create knowledge, where positive values might indicate effective knowledge generation and negative values could indicate lesser or ineffective knowledge creation. Curves and areas. Human domain expertise, blue area. This area suggests that traditional knowledge creation heavily relied on human expertise, particularly when less data was available or when the technological tools were relatively primitive. Data availability line, red curve. This line represents the increasing availability of data over time. As technology advances, more data becomes available, enhancing the potential for knowledge creation. Data-driven knowledge, yellow area. As AI technologies evolve, particularly with current and future AI applications, there's a shift toward knowledge creation increasingly being driven by data rather than solely by human expertise. Interpretation and insights. Transition from human-driven to data-driven. The graph suggests a transition phase where the role of human domain expertise is gradually complemented and in some cases overtaken by data-driven approaches. This shift is depicted by the red curve that shows an increase in data availability enhancing AI's capability to generate knowledge. Impact of AI and machine learning. The increasing slope of the data availability line coincides with the advancements in AI and machine learning technologies. Tools like self-driving cars and natural language processing algorithms represent peaks in data-driven knowledge creation, relying more on vast datasets and less on direct human input. Legacy tools to advanced applications. Starting from legacy IT monitoring tools which rely more heavily on human interpretation and intervention, the map shows a progression toward more sophisticated, autonomous systems like AI-driven diagnostics and predictive analytics, which rely on large-scale data analysis. Practical implications. Business and industry. Understanding this transition is crucial for businesses and industries as they plan their investments in technology. Companies need to balance between harnessing rich data sources and maintaining valuable human expertise. Policy and education. For policymakers and educational institutions, this map underscores the importance of curriculum and policy adaptations that focus on data science and AI skills, preparing a workforce that can thrive in a data-driven knowledge economy. Innovation and development. The map also highlights areas ripe for innovation, suggesting that as data availability increases, there is a greater opportunity to develop new AI applications that can push the boundaries of what automated systems can achieve. This knowledge creation map thus provides a conceptual framework for understanding how the evolution of technology and data availability are transforming the landscape of knowledge creation, emphasizing the shift from traditional, human-centered methods to more automated, data-driven approaches.
Okay, so the inclusion of self-driving cars on there is kind of a red flag for me, because it's like you always hear like, oh, we're going to get self-driving cars in 5-10 years from now, and then the time goes by and what we get is like some 1950s style robot that has always existed. It's just like people are allowing it to do more things right now, and it can't actually do anything that's technologically important to progress. So anyway, that's kind of what I think about that, and that kind of introduces some skepticism. Could you please give me some examples of like real world things where this diagram, you know, like really would hit home a lot better? So like if you were to replace self-driving cars on the diagram with a list of 10 more compelling examples, what would those examples be? ChatGPT would probably be on there. Recommendation algorithms maybe, but recommendation algorithms are a red flag too, because they do, in my experience, recommendations are very bad. Like I want a diversity of things. I don't want to be.
You raise a valid point about the practical impact and tangible progress of hype technologies like self-driving cars.
Yeah.
Let's explore alternative real-world examples that better showcase the transition from human expertise to data-driven AI systems, which can be substituted in the diagram to offer a more rounded perspective. Natural language processing, NLP, chatbots, and virtual assistants. Advances in NLP have significantly improved the functionality and user experience of chatbots and virtual assistants, making them more adept at understanding and processing human language. Healthcare. Diagnostic algorithms. AI systems that analyze medical images, like MRIs and X-rays, to detect diseases such as cancer with accuracy rates that often exceed human performance. Personalized medicine. AI-driven models that analyze patient data to predict the best treatment plans tailored to individual genetic profiles. Finance. Algorithmic trading. AI algorithms that can analyze market data and execute trades at speeds and volumes unattainable by human traders. Fraud detection systems. Machine learning models that detect patterns indicative of fraudulent activity more efficiently than manual monitoring. Retail. Personalized recommendations. AI systems that analyze consumer behavior data to provide personalized shopping recommendations, significantly enhancing customer experience and business revenue. Manufacturing. Predictive maintenance. IoT and AI-driven predictive analytics tools that forecast equipment malfunctions and schedule timely maintenance, thereby reducing downtime and costs. Agriculture. Precision farming. AI tools that analyze data from satellite images and ground sensors to guide farming decisions like planting, watering, and harvesting. Energy. Smart grid technology. AI systems that optimize energy flow and distribution based on real-time data, improving efficiency and reducing waste. Transportation. Logistics optimization. AI algorithms that plan and optimize routes and schedules, enhancing efficiency in transportation networks. Cybersecurity. Threat detection systems. Advanced AI models that monitor and analyze network traffic to identify and react to security threats faster than human operators could. Content creation. Automated journalism. AI-driven platforms that analyze data and generate news articles on topics like sports results and financial updates, which are fact-based and require quick turnaround. These examples illustrate a shift towards systems where AI significantly enhances or replaces human decision-making by leveraging large datasets and sophisticated algorithms. Each of these applications demonstrates tangible improvements in efficiency, accuracy, and capability over traditional methods, underlining the real-world impact of AI technologies as depicted in the original knowledge creation map diagram.
All right, so yeah, these are better. Particularly notable is, you know, I'm talking to you right now, I'm talking to the AI, and this is actually a pretty impressive experience. The other pretty notable thing is the stuff I don't really know a lot about, but I'm sure, like, you know, manufacturing, energy, I'm sure like medical, those are all legit. Healthcare, stuff like that. So like, okay, thank you. That is actually a lot better. But there is one more red flag on there, which is personalized recommendations. And don't get me wrong, like Amazon belongs on that list too. Like Amazon is kind of a miracle. But my experience with personalized recommendations is that they just try to put me in a bubble, or they're not accurate. And if I just turn them off and don't get any recommendations, I actually find better content, and the recommendations just like don't work, and all they want to do is feed me propaganda, or basically like the worst of the worst on the platform. Like they don't care that I get high quality information. They care that I get like whatever the richest person on the platform wants me to see, whether I like it or not.
You bring up some really crucial points about the limitations and challenges associated with AI-driven personalized recommendations. Your concerns are shared by many users and highlight significant areas for improvement and how these systems are designed and deployed. Let's delve into the issues you mentioned and consider ways these systems might evolve to better serve users. Challenges with personalized recommendations. Filter bubbles. Problem: AI systems often create filter bubbles, a state where a user is only exposed to content that aligns with their past behavior or preferences, potentially isolating them from new or contrasting perspectives. Potential solution: implementing algorithms that intentionally include diverse and contrasting content to challenge users' views and expose them to a broader spectrum of information. Accuracy and relevance. Problem: recommendations may not always align well with user interests, either because of poor algorithm design or insufficient understanding of user preferences. Potential solution: enhancing user profiles and preference models by allowing users to provide explicit feedback on recommendations, which can be used to refine future suggestions. Commercial bias. Problem: there's often a commercial bias in recommendations, where platforms prioritize content that maximizes their revenue, e.g., promoting content that keeps users engaged longer or content from paying advertisers. Potential solution: greater transparency about why certain recommendations are made and giving users more control over the factors that influence what they see. Quality of content. Problem: the emphasis on engagement can lead to the promotion of sensational or low-quality content. Potential solution: introducing quality metrics that assess the substance and reliability of content, integrating these metrics into recommendation algorithms. Forward path for AI-driven recommendation systems to truly benefit users: they need to be designed with a strong ethical framework that prioritizes user welfare, transparency, and control. Here are a few strategies that can help. Ethical AI design: developing AI with an ethical framework that prioritizes the user's well-being and privacy over platform gains. User control: allowing users more control over the recommendation algorithms, such as adjusting their own preference settings or opting out of certain ad collection practices. Regulation and standards: implementing regulations that require transparency in AI operations, particularly in how data is used and how decisions about content recommendations are made. Continuous feedback loop: systems should continually learn from user feedback to improve the accuracy and relevance of the content being recommended. By addressing these challenges, AI developers and platform operators can work towards systems that not only respect user preferences and privacy but also contribute to a more informed and diverse public discourse. This approach will help mitigate the issues you experienced and hopefully lead to more meaningful and useful recommendation experiences.
Okay, so that's the answer to that. Sorry, and I'm doing exercises. I'm habit stacking, so I'm doing exercises while I'm doing this, but that's okay. So let's continue. We could represent the same dynamics in the knowledge creation map from a timeline perspective. Over time, we observe both network and cloud infrastructures that the complexity and the SLA demands grow. Sorry, I get I get gagging in the morning. That was gross. I wish I could have paused, but I was doing a arm exercise, so my hand was occupied. So I'm going to do another exercise here quick. 8 reps. 1, 2, 3, 4, 5, 6, 7, 8, and continue. Infrastructures become increasingly critical as we collectively progress in the digital transformation, and at the same time, those infrastructures are becoming more complex to build and operate. It is no longer about large monolithic systems, but distributed microservices architectures with multiple moving parts, any of which may fail. Over time, the required operational knowledge to manage such infrastructures is growing. We could even argue that exponentially. A gap between the need and what human expertise can possibly deliver is growing. Suppose we do not leverage data and ML techniques. In that case, this gap will jeopardize the applications and services that rely on adequately operating the network and cloud infrastructure. Even if we apply some ML techniques, such a gap will likely still exist over time. There is a need to transition towards a truly data-centric operation approach, which could fundamentally change the economics of how operational knowledge is built to maintain and operate such complex infrastructures. Along with such vast amounts of data will be the application of deep learning techniques to extract such knowledge from the data. This perspective may generate controversy because the economic disruption may be associated with the need for fewer people. There will undoubtedly be a need for fewer people compared to the scenario where we tried to address the same complexity with just people, which would very likely not even be possible. However, there will be a transition from low knowledge tasks to algorithms and automated processes, releasing people from doing such tasks to focus on the more complex and added value knowledge generation. Whether you agree or not with this perspective, I believe you will certainly agree with me that the combination of complexity and stricter SLA demands to the network infrastructure will result in use cases the human cannot address. The only way to deliver on the I'm doing the exercise again. On the end user's expectation would be to shift towards a data-centric operation approach. And that noise might require a explanation of what kind of exercise I'm doing. I am doing a wrist exercise, but it's moving my. I have a special device, and I'm moving my palm backwards, and I have like an elbow issue, so it's like I'm probably doing too much. It kind of triggered a little bit of a pain, is what that was. It was not a pleasure. All right, so key takeaway: deep learning combined with techniques such as reinforcement learning will help disrupting the economics of building network and cloud operational knowledge. It is the data, stupid. We have dedicated a good portion of this book to explaining a broad spectrum of algorithms within the scope of machine learning. We use these algorithms because we have specific problems to solve and certain input data. We choose an algorithm to build or train a model that allows us to obtain specific outcomes, classification, regression, generation, etc. Furthermore, it would appear through this process that the model is the critical piece in this puzzle. Indeed, the ML models play a fundamental role, but the key is to the data, not the model. Over the past years, most of the focus in terms of research has been around models and the ability to design and train more complex models that will enable more profound insights. However, over the past couple of years, the tide has changed. There is a more substantial realization that the critical determining factor in the success of any project is not the model, it is the data, the quality of the data, and the degree to which the data represents the reality we are trying to model, diversity, lack of hidden bias, etc. And that sounds like a very hard problem, I just got to say, because if you just go out and look in nature, which I like to do sometimes to take photos, there is a lot of detail out there, and data is always going to be missing most of it. There is a growing trend around data-centric AI. It is not to diminish the role of the ML model, but to emphasize that by investing more effort in maximizing the data quality, we can obtain the same or better results with simpler models. And then the other thing that is important to understand is, the goal isn't necessarily to just maintain the status quo. So like the data could be telling you, this outcome is what you need. And everything could be right. The data could be right. The model could be right. But you're perpetrating a system that is leading to poor outcomes. So, you might need the solution might be radically different than it's like is the goal just to perpetrate a malfunctioning system, or is it to get to a better place? If it's to get to a better place, then no matter how good your data is, no matter how good your model is, you get the right answer. But like self-driving cars is a great example. Like, do we as citizens want to just sit in a car all day? Like, why not just work from home? The people who can, like, that would change society just as drastically. So I think that's a good example. When the data does not have the right quality and is noisy, we need more complex models that can learn the patterns and discard such noise. Suppose we can minimize such noise by applying pre-processing techniques, being more selective on the data, or improving our data collection mechanisms. In that case, we will be able to build and train simpler models that will not have to deal with such noise. The tide has changed from a model-centric AI towards a data-centric AI. If you look through the table of contents of this book, it is primarily, if not exclusively, focused on algorithms and models. I firmly believe in the importance of data-centric AI and the impact of having the right data quality. However, from the perspective of what I want to help you with in this book, I find it very important that you understand the different types of problems and algorithms, which is the reason for such a focus in the book. This does not mean models are the most important. However, the concepts behind those models, I'm a little hot here, so I will cool down, are the most novel and likely challenging. In my opinion, for you to grow as a network and cloud professional. So the concepts behind those models are the most novel and likely challenging. So learning the models, So models, data is, So it's really important. The author finds it for you to learn the types of problems and algorithms. but it does not mean that the models are the most important. But what it does mean as a learner of MLI is that learning the models is the most challenging and novel thing you'll do. So therefore, learning the math behind the models is more important than the data. But when you're actually applying it, now the models don't matter at all. It's all about the data. But as a learner, you have to learn this less important thing in order to be able to adjust your focus on the more important things. However, the concepts behind these models are the most novel and likely challenging, in my opinion, for you to grow as a networking and cloud professional. I am not sure if you will apply these technologies yourself. However, if you do, you should remember, hence the intent of this section, that data quality is way more important than you may think, and investing the right time and effort in it will definitely pay off. We will see some examples of that in the practical use cases section. You will experience soon, if you have not experienced it already, that in any ML project you may end up spending likely between 70 and 80% of the time in the data pre-processing tasks, cleaning, visualizing, removing outliers, filling data gaps, normalizing, rescaling, tokenizing, re-encoding, etc. This is where, no matter what, data scientists spend most of their time. Once data is ready and clean, the remaining 20 to 30% of the time will be invested in the model selection and training part. In this book, we have invested most of the time in explaining the magic that happens between 20 and 30% of the time. But you should remember that in any ML project you get involved in or task to embark on, most of the time and effort will be to get there. It is expected and now more than ever widely recognized. It is the data stupid. It is in the data where the magic actually happens. Key takeaway: data quality is above anything else in a machine learning project, period. How to explain what is in the black box. We have reviewed many ML algorithms, some of which are highly sophisticated. Models such as neural networks with multiple layers composed of millions of parameters will make complex decisions based on the input data provided. Consider the following situation. You are a network operations engineer responsible for a large cloud infrastructure. As part of a transformational initiative, you and your team have implemented a closed-loop automation solution. An ML model has been trained to detect what type of problem is happening. Based on that, an automated action will be triggered, such as restarting a node, resetting an interface, redirecting a customer connection to a backup location, etc. This has been a very promising project in which there has been involvement from all the team. The ML model in use, a neural network with 4 layers and about 500,000 parameters, 500,000 parameters, has a validation accuracy of 96%, which all consider being very good. It is expected to detect automatically and resolve many basic issues in your cloud infrastructure that otherwise require manual effort. So far, so good. Promising. The system has been moved to a production state and has been working for about 2 weeks with no issues so far. A few network issues happened, and the model detected them as expected and activated the intended action. On Tuesday at 11:30 a.m., however, the model detected a specific condition and triggered a node restart, which caused a relevant service outage. Some post-mortem analysis shows that the model detected the wrong problem. For example, misclassified the situation, leading to the wrong action. Because this caused service interruption at peak hour time, there is some escalation to the CTO who rightfully asks, why did this happen? The answer is crickets. No one knows exactly why this occurred. No one knows why the model made the wrong choice, but the fact is that it did. It is extremely difficult to know, if not impossible, why a neural network such as the one used in this case provides a specific output. It is really a black box. So back to our scenario, the CTO asked, why did this happen? And the only response was, we do not know and we likely cannot know. I mean, the answer is probably the data, honestly. What will happen next? The solution everyone is proud of will be taken out of production. You may feel I am over dramatizing the situation, which is certainly my intent. However, this situation illustrates one of the key challenges with ML that you should be aware of: explainability or lack thereof. In the example above, it was apparently a good model on paper with a good accuracy of 98%, but even if it was 99% or higher, all these models are statistical, and at scale, all will fail. 2 out of 100 times the model makes a decision, it will be wrong. You need to be ready to tackle those 2 bad decisions. You should be able to explain them. Unfortunately, the explainability of a model is usually inversely proportional to its complexity. Simple models for simple tasks have excellent explainability properties. A logistic regression sets a straight line between the classes. And I'm having my morning. In the mornings, it's hard for me to speak in the mornings. I need a break. I'll be right back. All right, I am back. I am in a seated position, which is a lot better. All right, so a logistic regression sets a straight line between the classes. It is easy to explain why it made a particular decision. A deep neural network with millions of parameters can make very complex decisions, but at the same time, those decisions are almost impossible to explain. Sometimes we may need to sacrifice model complexity and accuracy in favor of a system with more easily explainable decisions. There is also a cultural shift that will be required. Today, most people may ignore the challenges around machine learning model explainability and may be surprised if they face a situation such as the one described above. As everyone becomes more familiar with ML algorithms, it will be less of a surprise that certain decisions are difficult or impossible to explain in the context of networking and clouds. It may, over time, be factored in already in the decisions about project deployments. For example, we may find normal the lack of explainability. In the meantime, we need to double efforts to implement mechanisms that improve explainability and provide the level of confidence necessary for management and executives to build trust in the benefits of machine learning in their network and cloud infrastructures. On the other hand, and this is a personal belief, we demand a certain degree of explainability to machine learning decisions that that's a good point, actually, that we very likely do not require of humans. That's a really good point. And I've heard that point made as well. Like, imagine a world, like, what's the rate of, what is the rate of car accident deaths? So in 2023, there were nearly 4,000 fatal car crashes. Now imagine a world where there were only 3,000, where there were only half of that. That would be a better world. There's less people dying in fatal car crashes. But let's say that world came to us through a giant evil mega corporation that people demonize. That corporation is going to get sued, and they're going to get sued a lot. Even though they created a positive outcome, the fact remains that there are still thousands of people dying a year, but that now they're dying from this product that can be taken to court. So yeah, that's kind of the classic example of that, and I think that's a pretty legit example. But at the same time, it's and then imagine a world like this. So there are 3,855 fatal car crashes a year in Texas. Imagine a world where there's 10,000 car crashes, but rather than them being fatal, they cause minor damage. Like you have kind of like a knee problem now. You have, like maybe some kind of like scarring from something, or like, imagine a world like that. Now those 3,855 people are alive. They're very badly injured, and then there's more people that are injured in a very minor way. When does that balance out? When does it? How do the numbers work in that case? There's fewer deaths, but there's more lifelong injury and disfigurement. So, yeah, they're hard problems for sure. And chronic pain. You might be tempted to say, oh, well, what do I care if I have like a burn damage or like a little bit of a limp or something? Well, where it gets tricky is treatment of chronic pain. If every moment of your life is like a intolerable hell, people commit suicide all the time, and it's sometimes not the most illogical thing in the world. So if you're dealing with a lot of chronic pain and just feeling bad all the time, that could be worse than death. And to a lot of people who commit suicide, it is. So, they're very hard problems. And, when it comes to a human decision, we can have empathy for the human. But when it comes to machine learning, a robot, it's harder to do so. So if a human decides, oh, there was a weird situation in the road, I decided to kind of swerve out a bit, and I didn't see the person there. I cut them off, and I caused a car accident. There might be the humans definitely made a mistake, but imagine if a automated product did that, you would say the product malfunctioned. It made a decision that is unacceptable, and that is, the human who did that would probably be back on the road after a while. But yeah, but I guess what I'd like to do is wrap up this thought and continue reading. So to wrap up the thought, what I'd say is, yeah, I highly agree that there is a degree of tolerance to machine learning mistakes that needs to be granted, but it needs to be measured and granted in a way that is where it outperforms. As long as the machine learning is outperforming the humans, and not just outperforming the humans in perpetrating broken systems, but outperforming the humans in incremental improvements to these broken systems, and ultimately leading to better systems, then even if the machine learning makes mistakes, I think the benefits outweigh the negatives. And we see that with ChatGPT as well, because ChatGPT gives wrong answers sometimes. It just gives, the consensus of what the answer is. It doesn't give the right answer. And more often than not, the consensus of what the right answer is the right answer. So it's a net good, in my opinion. Frequently, when we refer to self-driving cars, we tend to put the car in impossible situations to understand what it would do. And humans get in that situation as well. What if there is an elderly person and a child crossing? What would the car do if it cannot stop? So let's say that it's an icy road. It didn't account for that, and now the car is just skidding, and it has no ability to stop. Well, there is no good outcome. But there would be no outcome either if it was a person driving a car. However, we want to know what the machine would decide and why. No matter what or why, it would be a disaster. I mean, that's the case with humans as well too. Like, we design systems, we design walkways for people to use. We give citations to humans that make poor decisions on the road and don't follow the rules of the road. So it's the same. Similarly, we want to know, honestly, I think when it comes to self-driving cars, it's just the technology of self-driving cars is not there. Similarly, we want to know why a neural network made a particular choice, but we do not know in detail why the human brain made a particular decision. Humans also make mistakes, and sometimes it may not even be possible for a person to explain why he or she made such a mistake. All this is debatable and likely crosses the boundaries of philosophy and neurology, so I will not go further as I am not an expert in either discipline. At the very least, we can review some techniques used in machine learning to help explain or provide visibility of the decisions taken. My goal is that you get familiar with these terms and know the basic principles behind them. All right, that's an admirable goal. So I'll advance the bookmark. Check the time. All right, and I'm actually feeling good, so I'll keep going. So the first term and principle behind decisions that a machine learning model so the first term and basic principle, so the first technique used in machine learning to help explain or provide visibility of the decisions taken is local interpretable model agnostic explanations, also known as LIME. The principle behind local interpretable model agnostic explanations is that while a use case and associated variables may be globally very complex, for example, highly linear, when we zoom in on a specific region of the space, the behavior may be much closer to a linear one. Therefore, we could possibly make a local linear approximation of such a specific region and use that approximation to explain or understand decision criteria. So the second technique used in machine learning to help explain or provide visibility of the decisions taken is distillation. Distillation is a technique used in machine learning to transfer knowledge from one model to another, usually from one larger model to a smaller one. In distillation, there is a teacher model and a student model that will tend to learn from the large model. We can use this technique to have the student model be the model we use to explain the larger one, the teacher. And the next technique for explaining ML decisions is Shapley additive explanations. The concepts behind Shapley values derive from game theory. We try to identify how the various input features contribute to a specific model output, prediction, classification, etc. Somehow it is about understanding the relative feature importance of a model. Shapely values are helpful for both local and global interpretability. Computing the Shapely values is a very complex process that may take a long time to be executed, from many minutes to days. Key takeaway: you must think carefully about how you will explain the decisions made by your model to your manager. If you cannot, then maybe you need to pick up a simpler model. Right. And I would even go as far as to say you must think carefully about who your manager is. If your manager can't tolerate, if your manager doesn't know and expect that you will be using and like the first thing I would do is classify your manager as somebody familiar with AI and somebody not. But honestly, that's not a helpful classification either. Um, yeah, you just like if you're on a team and your manager's goal is to implement AI, um, that's one scenario. But another scenario is if you're just kind of doing this stuff on the side because you think it will help. That's a scenario where things absolutely can't go wrong. So that's a scenario where you have to just by default do really simple things. All right, so ML Ops. Machine learning is an acronym-rich field, and ML Ops is yet another new term you should at least be familiar with and understand what it is about. I will not explain techniques in detail within ML Ops since there is plenty of literature on the subject. We have evaluated multiple algorithms that, when trained with the correct data, will result in a model ready for inference. However, the process does not end here. Your trained model may be adequate for the data you used to train it, but data is constantly evolving. Data drift is the phenomenon by which properties of the data may evolve, the distribution of classes, the characteristics that result in certain classes, etc. All this will result in your model being less and less adequate for the job it was initially trained for. That means you will need some mechanism to evaluate your model's performance with new data constantly. You should retrain the model with the new data if the performance degrades beyond a certain point. The life cycle of your ML project will require not only the initial training and deployment, and most likely in a Kubernetes environment, but also monitoring the model's performance, retraining, redeploying, and so on. This process is what we refer to as ML Ops. ML Ops is the DevOps for ML models for practical purposes: continuous delivery, continuous monitoring, and when required, continuous training. It is essential to distinguish the term ML Ops from AI Ops. AI Ops is the set of techniques intended to monitor a cloud infrastructure using AI/ML techniques. ML Ops is the continuous process of managing the ML model's lifecycle. An ML model is by definition ephemeral because it is only valid if the data stays static, which will rarely happen. When you become more familiar with the field, you will find plenty of open source ML models, even pre-trained ones, that organizations make available for the wider community. You could think those models are precious and wonder why they give away all that value. Considering what you know now about the dynamic nature of an ML project and the fact that the value of a particular instance of an ML model is ephemeral, you can understand that while very useful for experimentation, these models are not that valuable in themselves. The more significant value is on the data used to generate them. The updated dataset with new data and the parameters and conditions used to train those models. This is rarely, if ever, made publicly available, and it is the secret sauce they will keep. So it is the data and the process that are extremely valuable. The trained model itself is an artifact whose value will diminish over time, hence the importance of a continuous delivery dash continuous integration ML ops approach. Key takeaway: machine learning projects do not end when a model is deployed. There is a continuous process and life cycle of the models. ML ops is the framework that helps manage such life cycle. How machine learning learns from nature. All right, so this might be a good logical stop point. I'm usually only good for an hour doing this. It's a lot to read out loud for an hour. I think people don't realize that. I think people that think, oh, why can't I be productive, don't realize that the reason you can't be productive is because you haven't been productive for a long time, and you're expecting yourself to just do 8 hours of something. It's like the most you can do is 5-10 minutes right now, because imagine doing squats or push-ups or like that. It's like you're not, like, you have to start small, and eventually over time you can be productive at the levels you think you should be. It's just right now you're not trained enough to get there. So like that's where I'm at, is like I can only really do an hour right now, because it's just hard to read out loud for an hour, and I think people think it's easier than it is. I know I did. I know I did for sure. All right, so that's it for this video. Stay tuned for how machine learning learns from nature, which should be a fascinating chapter. So thanks for watching, and see you in the next one.